In the previous few lectures, we have been discussing forced convection, that is forced convection in the limit of high Peclet number, where the Peclet number is the velocity times the characteristic length divided by the diffusion coefficient. And we solved problems of flow past a flat plate, of heat conduction from a plate in the limit of high Peclet number, in a pipe, around a particle, around a gas bubble. What we found was that the correlation, the effect of the surface. So, if you have a heated surface in a flow and the Peclet number is large, that means that the velocity times the diameter divided by the diffusion coefficient is large. You would normally expect convective effects to dominate compared to diffusive effects. However, if you neglect diffusive effects altogether, then there is no transport from the surface, because there is no convection from the surface, because at the surface itself there is a no penetration condition. Okay. The fluid cannot travel perpendicular to the surface in a reference frame moving with the surface. Therefore, there is no convection perpendicular to the surface, and you require transport perpendicular to the surface to transport heat, mass perpendicular to the surface into the fluid. Therefore, we found that even in the limit of high Peclet number, there are regions close to the surface which of thickness small compared to the characteristic length. We had called that the boundary layer thickness delta, where convection and diffusion are comparable, where there is a balance between cross stream diffusion and convection in the streamwise direction. And at these locations, there is a sharp temperature gradient which results in transport. The rate of transport and the boundary layer thickness depend only upon the boundary condition at the surface, or rather the scaling of the diffusion coefficient of the boundary layer thickness, or the Nusselt number or the Sherwood number, the rate of transport, the scaling with respect to Peclet number. Okay. So, in the limit, as the Peclet number becomes large, this boundary layer thickness becomes smaller and smaller in such a way that there is a balance between convection and diffusion. The scaling of these boundary layer thickness or the transport rates with the Peclet number depends only upon the boundary conditions. For a zero velocity boundary condition at the surface, the boundary layer's thickness scales as Peclet number to the minus 1/3. The coefficient in front does depend upon the configuration. However, the scaling Peclet number to the minus 1/3 does not depend upon the configuration. And in a similar manner, for a no slip condition at the surface, where the tangential velocity has to go to 0 at the surface, the Peclet number, the boundary layer thickness scales as Pe power 1/3, power minus 1/3. It decreases to 0 as Pe increases, and the transport rates scale as Pe power plus 1/3, or rather the correlations, the Sherwood or the Nusselt number, they scale as Pe power plus 1/3. If there is a mobile interface, so that the tangential velocity is non-zero at the surface, okay, if you have a mobile interface where the tangential velocity is non-zero at the surface, then the boundary layer thickness scales as Peclet number to the minus half. Coefficient depends upon configuration, but the scaling with Peclet number is Pe power minus half in all cases, and the Nusselt number or Sherwood number scales as Pe power plus half. Once again, the coefficient depends upon the configuration, and it has to be calculated for each individual configuration, and I showed you an example of how this calculation can be done. Here we will start another topic also in forced convection. Okay, high Peclet number, okay, which is what is called Taylor dispersion. Okay. This is the dispersion, the axial dispersion in a pipe, okay, the axial dispersion in a pipe, once again at high Peclet number. Okay. So, the typical configuration looks something like this. You have a pipe in which there is a velocity profile. Okay, so, let me draw that better. Okay, some velocity profile, it should be axisymmetric. Okay. Okay. Of diameter d. Okay. I will call the streamwise as the x direction. The radial direction is in the cross section. Okay, the radial direction is in the cross section. Okay. And the radius is 1/2 of the diameter, which I will call r. Okay. And this is relating to the axial dispersion, the dispersion along the axis, okay, the dispersion along the axis due to forced convection. Okay. And this is calculation is valid under certain assumptions. Okay. One is that the Peclet number is large. Peclet number based upon the pipe diameter and the average velocity. V average d by d is large, okay. Okay. Where d is the capital D is the molecular diffusion coefficient, okay, where capital D is the molecular diffusion coefficient. Okay. Second, at any downstream location, okay, the concentration variation across the cross section is much smaller than the average concentration. Okay. Now, what does this mean? Okay. So, if we take for example, a typical time scale, okay, so characteristic time diffusion time across a distance d, where d is the pipe diameter, will scale as d square divided by the diffusion coefficient, okay, the length square by diffusion coefficient. We have seen that numerous times when we did separation of variables for transport problems. We saw that the characteristics time scales as the diameter square divided by the diffusion coefficient. Okay. That is the characteristic time for which diffusion is taking place. Okay. What is the characteristic length for diffusion? Okay. What is the characteristic length over which diffusion is taking place? Okay. In time, okay, I will call this as the diffusion time. Is equal to d square by the diffusion coefficient. Okay. Downstream length travelled, okay, is going to be equal to the average velocity times the characteristic length, characteristic time. Okay. The amount of the length travelled from the start, okay, in this characteristic time taken for the diffusion across the cross section is going to be equal to V average T d is equal to V average d square by d. Okay. That is going to be the length travelled. Okay. Okay, the average, therefore, the average length beyond which the concentration has equalized across the cross section. Okay. The average length across which the concentration has equalized across the cross section, okay, length required for diffusion across the cross section, L is equal to V average d square by d, okay, which implies that, okay, the length for diffusion by d is equal to V average d by d, and this is equal to the Peclet number. Okay. So, this is the length taken for the concentration to equalize. Okay. Here we are assuming that the concentration variations are small, that means that the length that it has travelled is much larger than the diffusion length required for the concentration to equalize across the cross section, and that is valid for L by d much larger than the Peclet number. Okay. From this simple calculation, just calculating the diffusion time across the cross section, you multiply that by the velocity, you get the diffusion length, the length after which there is equalization of concentration across the cross section. And we are assuming that the concentration variation across the cross section is much smaller than the average concentration. That means that the concentration has almost equalized across the entire cross section. That implies that the length of the pipe divided by the diameter has to be much larger than the Peclet number. Okay. So, we are talking about high Peclet number limit and when the length is large. Okay. The other assumption that is made over here, okay, the other assumption that is made over here is that length scale for variation in the axial direction, okay, x direction, is much larger than the diameter. Okay. The length scale for the variation, that is the length over which, so if I plot the concentration as a function of length, okay, so concentration as a function of length, average concentration, okay, you get some variation. Okay. This length scale for the variation has to be much larger than the pipe diameter, that is over a distance of equivalent to the pipe diameter, there is not that much concentration variation. Okay. So, this implies that derivative of the concentration with respect to radius will always be much larger than the derivative with respect to length, because the length scale over which the concentration is varying is much larger than the pipe diameter. Okay. So, that is the other assumption that is made. Okay. And since we just showed that the travel time is much larger than d square by d, okay. Therefore, length is much larger than V average d square by d, okay, and we get the same condition. This implies that L by d is much larger than the Peclet number. So, it is the same condition that we got over here. Okay. This approximation is also valid for the same condition that we got here. Okay. Therefore, I am sorry, this should be the diameter, not the diffusion coefficient. Okay. So, let me write that correctly. Okay. So, therefore, the length scale over which there is diffusion is taking the length scale for concentration variation along the length of the pipe is much larger than the pipe diameter. Okay. So, that is the other assumption that we make. Okay. Okay. So, why should this dispersion happen? Okay. So, let us look at physically at what happens in this. Okay. So, I have a pipe here. Okay. And let us say that I had a plug flow. Okay. There was no variation across there was no cross stream variation. Okay. In that case, for a plug flow, okay, the velocity is almost a constant. The velocity is a constant for a plug flow across the pipe. Okay. Of course, this is unphysical. You cannot have non-zero velocity at the surface, but let us just assume that for a plug flow, the velocity is a constant. Okay. So, I have put some pulse over here. Okay. As it travels downstream, okay, because the velocity is a constant, the pulse will continue in the same manner. Okay. Okay. If I put a pulse here, as it moves downstream, the pulse will continue in the same manner. Okay. So, okay. If there were no diffusion, then there would be no dispersion. Okay. If there were no diffusion, the only change could be due to molecular diffusion. Okay. And if I plot the concentration, okay, if it is something like this over here, the concentration looks something like this over here. Okay. The only way that it would spread at this location is due to molecular diffusion. It would become slightly, okay, distance would become slightly larger and the height would become slightly smaller only due to molecular diffusion. On the other hand, if I had a laminar flow, okay, okay, we know that the laminar flow velocity profile is parabolic. Okay. We know that the laminar flow velocity profile is parabolic. Okay. Okay. So, if I injected a pulse at this location, okay, if I injected a pulse at this location, okay, same profile. Okay. Okay. Just sharply peaked at the origin. If I go a little later, you will see that this has to actually deform. In a laminar flow, this has to deform. Okay. And if I plot this, okay, in fact, this is not quite correct. The velocity has to be 0 at the walls. So, the pulse has to come all the way back to 0. Okay. So, it should actually look something like this. Okay. Okay, after some time, because the center of the pipe is moving at a higher velocity, the wall is 0. So, the pulse will expand like this, and if I plot the concentration profile, okay, you would get a much wider concentration profile going all the way from here. Okay. You would get a much wider concentration profile. Okay. And this stretching of the pulse, this stretching of the pulse by the laminar flow also results in cross stream diffusion. Okay. The stretching of the pulse by the laminar flow also results in cross stream diffusion, which gives rise to dispersion in the axial direction. Okay. So, you get a much larger stretching if the velocity is larger. Okay. You get a much larger stretching in this case, and then there is cross stream diffusion, which tends to equalize the concentration across the pipe. Okay. There is cross stream diffusion that tends to equalize the concentration. The diffusion coefficient, or rather the coefficient in the axial direction for this laminar flow. Okay. Okay, first things first. Okay, so, for this pipe, so this is the diameter, okay, and V average is the average velocity. We know that the x velocity is equal to V average into 1 minus r by r the whole square. Okay, that is a parabolic velocity profile for a laminar flow in a pipe. Okay. I am sorry, it should be 2 times V average, because the maximum velocity in a pipe is 2 times the average velocity. Okay. So, it is 2 times V average times 1 minus r by r the whole square. Okay. And the concentration equation is going to be partial C by partial T plus V x partial c by partial x, okay, is equal to d into 1 by r d by dr of r partial c by partial r plus partial square c by partial x square. Note that I am using x instead of z, sometimes we use z instead of, okay. So, I am using x instead of z over here, x is the axial direction. Okay. The velocity is separated out into two parts, okay. Vx is equal to V average plus Vx prime, okay. Vx prime is the difference between the average velocity and the local velocity, okay. So, V average is 1/2 of the maximum velocity, okay. So, that is V average, okay. The difference between those two is Vx prime, okay. The difference between those two is Vx prime, and that implies that Vx prime is equal to V average into 1 minus 2 r by r the whole square, okay. Okay, I just subtract out 1 V average from the total velocity, okay. So, that is Vx prime. Similarly, the concentration is also expressed as C is equal to C average plus C prime, okay, where C average is the cross section averaged concentration, okay. Just as V average is the cross section averaged velocity, C average is the cross section averaged concentration, okay. So, the cross section averaged concentration, okay, once you average over the cross section, it no longer depends upon the radial distance. So, this is just equal to C of r, x and t, sorry, this no longer depends on the radius. So, this is only a function of x and t plus C prime of r, x and t. Okay. Where C average is equal to the cross section average concentration, okay, 1 over the area, okay, and I will assume for now that the concentration is not a function of the azimuthal angle. So, I will get the elemental area in 2 dimensions is 2 pi r dr into c of, okay, r, x and t. Okay. So, once I have integrated over r, there is no dependence on r on the left side. Therefore, the C average that I have defined here is only a function of x and t. Okay. What this also implies is that the cross section average of both Vx prime and C prime is equal to 0. Okay. The cross section average of both Vx prime and C prime is equal to 0, that is 1 over pi r square integral 0 to, this should be 0 to r, 2 pi r dr into C prime of r, x and t, okay. C minus C average, okay. When I integrate C, I get C average. Therefore, when I integrate C minus C average, this has to be equal to 0, which is also equal to the cross section average of the velocity, okay. Integral 0 to, divide by the area, integral 0 to r, 2 pi r dr into Vx prime, okay. Both of these are equal to 0. Okay. Now, in Taylor dispersion, we are dealing with the axial flux, okay. We are dealing with the axial flux, okay. And the axial flux can be written as the cross section average of the total flux, okay. So, therefore, the axial flux, okay, is written, okay, we want an effective equation of the form d effective into partial C average by partial x, okay. So, if the axial flux were written of this form, we want to know what is this dispersion coefficient, the effective d effective, the effective dispersion coefficient if you write the axial flux in this manner, okay. And of course, this is equal to the cross section average 1 by pi r square integral 0 to r 2 pi r dr into j, which is a function of r, x and t, okay. the flux in the x direction, cross section average gives you the average flux, and we want an expression for the average flux in terms of the average concentration gradient in the axial direction. Okay. Now, as you know, the flux consists of two parts. One is the convective flux due to the flow velocity, the other is the diffusive flux. Okay. In a reference frame moving at the same velocity as the fluid, okay, in a reference frame moving at the same velocity as the fluid. Okay. So, first of all, the convective flux J x is equal to V average V x c plus, okay, minus d partial c by partial x. Okay. We want the dispersion, that is in the reference frame moving with the average velocity. Okay. That means that in the reference frame moving with the average velocity, okay, the flux is going to be equal to, okay, you have to subtract out V average times C average, okay, in a reference frame moving with the average velocity. Okay. So, that is the flux in the x direction in a reference frame moving with the average velocity. The average flux due to the average velocity is included in the convective term, okay, and what we have here is only the diffusive term. Okay. What we are calculating here is only the diffusive term, therefore, or rather the dispersion term, not the average convection. So, I have separated out convection into average convection plus that fluctuation V x prime, and I want the flux that is in excess of the average conversion, that is C average times V average. Okay. So, I can write this expanding, okay, V average plus V prime, C average plus C prime, okay, minus d into partial C average by partial x, okay, plus partial C prime by partial x. Okay. Okay. Minus V average C average. Okay. So, that is going to be the flux in the x direction. Okay. And you can see this expands out as V average C average plus V prime C average plus V average C prime minus d partial C average by partial x, okay, minus d partial C prime by partial x minus V average C average, okay, and these two terms cancel out. Okay. When I take the cross sectional average, okay, J average, okay, integral 0 to r 2 pi r dr into V prime C average plus V average C prime. Okay. I have missed out a term here, so let me just include that. Okay. So, you can see that V average plus V prime into C average plus C prime. There is V average C average, V average C prime, V prime C average. So, I have to have another V prime C prime over here, okay, V prime C prime. So, plus V prime C prime minus d partial C average by partial x minus d partial C prime by partial x. Okay. So, this is the expression for the average flux. I will continue this in the next lecture to use this in order to calculate for us a dispersion coefficient. Okay. So, this calculation I will continue in the next lecture. I will see you then.